So, weak signal propagation reporter, or Wspr. Some of you will remember that I did a presentation on digital modes a while back, last year, and Wspr was one of the modes I covered. As I said earlier, I got a kit from QRP Labs out of Germany that really was a pretty nice kit, challenging, an endurance test somewhat, I would say, would be fair. Just about 100%, I think, through hole parts. So that way, from a soldering standpoint, not bad, but just a lot of putting together and fitting. One of the options that I chose was the the temperature-controlled crystal oscillator. That comes in as one not broken apart PCB. Yeah, where's that meter?
Yeah.
That actually you have to break apart carefully, and then you build an enclosure for the crystal, which is heated by a couple of FETs, running hot, basically. And then you put an enclosure over that, and then there's an enclosure underneath, and then an enclosure on top of all that. So it's basically trying to keep thermal stability there for the crystal. So a crystal will tend to drift, and the kind of cuts that we typically see will tend to drift negative, so down in frequency with heat. So they have a way to compensate it, bring it up, calibrate it. And then it has a huff and puff, and I'm sorry I don't remember who did it, if it was Bob or someone did a pitch on huff and puff.
It was Bob.
Yeah, frequency correction, so they actually go through that algorithm to adjust the VCO part of it. But typically I find that, and we'll see this a little bit later, that I've got zero drift on Wspr, which is great. That means both myself and the reporter on the reporting end are both in lockstep for the 2 minutes during the transmission. But let's get into what Wspr is again. It's a standard message frame format that has a 4-digit locator. So your grid, 4 of the 6 digits. Now you can put all 6 in, and there's an extended message to get the whole thing in, but the basic header is 4-digit locator. Your power in dBm, I skipped over call sign, so your call sign, of course, 4-digit locator, and the power in decibel meters. So in my case, it would be K0 WFS, EN34, and then 23 for 23 dBm, which is 0.2 of a watt. This particular kit runs with a single output at 0.2 of a watt max, and of course it can run lower. And we'll see what 0.2 of a watt can do for you at Wspr. It's more than you'd think. So the message components then end up being 28 bits for the call sign, 15 bits for the locator, and 7 for the power level, for a total of 50 bits altogether. Okay, so you've got in that message 50 bits. Now I'll jump ahead just a little bit here and to tell you that essentially this message is being broken up and being sent just a few bits at a time over a 2-minute period, or roughly a 2-minute period, a little bit less than that. So we're not talking about a high throughput, high bandwidth thing here. What we're talking about is high reliability, low bandwidth with a bunch of error correction, which I'll get into. Okay, so it's trying to do what we sometimes call in the IT world or computer world durable messaging. It's trying to make sure that message gets there by having a lot of redundancy and not pushing the limits of technology by any stretch of the imagination. Okay, so the forward error correction, this sounds like a big deal. As we'll see, it's not that big a deal, but non-recursive convolutional code with a constant length of 32 and a rate of 1/2. All right, I'm going to explain that in English best I can, but it's not as bad as it sounds. The number of binary channel symbols are 162. What that really boils down to is the whole message from start of transmission to end, is broken up into frames, but essentially it's 162 bits, with the redundant bits put in as parity bits to essentially ensure that every important data bit is at least flagged as invalid, and if you run into that case, which is rare actually. The keying rate, which is a little bit of a mystery in FSK, but essentially the way Wspr works is there's what was set up, because so many of these rigs were initially at-home rigs that were going to be triggered via audio. So the recommendation was to always run them on upper sideband and then run a dial frequency, right, that's 12,000 hertz lower than the center of the 200 hertz spectrum for Wspr for that band. Okay, now we'll get into that a little bit more, but essentially that's where the 12 comes from. The 8192 has more to do with how quickly it can go through its algorithm, which is only 3 steps, but it has to be able to crank through that algorithm between each symbol. Okay, so it turns out there's a shift operation, an XOR, and another shift, and so on and so forth. So that's got to happen pretty quick, but you end up with an effective rate of 1.4648 baud. I'm sure many of you remember 300 baud, 1200 baud modems. So 1.4648 is not a lot of baud. But again, you think of it in terms of sending 1 bit per frame with redundancy, you wouldn't need much anyway, right? If you were talking about a higher throughput, the message would just be out lickety split, and of course it's spread out in time. The modulation is continuous phase, which simply means that it's transitioning from tone to tone. So it's going for FSK with a 1.4648 hertz separation, which is also related to the symbol rate. The nice thing about Wspr is, because it only has 4 shifts at 1.4648 hertz in between them, it takes up an occupied bandwidth of just under 6 hertz. So your transmission is only taking up 6 hertz of bandwidth. Within that 200 hertz that you have as by convention to work within, that means a lot of people can be on simultaneously. And obviously, if they're in different parts of the world, they could be on the exact same setting, for that matter. So it's great for utilization of bandwidth. Much better than sideband. Obviously, single sideband is not the best example of utilization of bandwidth, but this is the other end of the spectrum. The synchronization really isn't so much an important thing, but we'll see that the real message is 50 bits with some padding, because of the way, long story short, this came out is it had to be a multiple of 9. You have 8 bits plus a parity bit. So you have a multiple of 9, you end up at some convenient numbers like 72, so on and so forth. Well, we'll see why they went to 81. But essentially, there's room for extension. So they had an extended message in there to put in there so that you could get the full 6-character grid. You could accommodate longer call signs than what they originally had allotted for. So a 2x3 wasn't, as I recall, wasn't fit in there, but 1x3s and 1x2s were. So those were just extra TBD kind of bits that were left over anyway. The data structure, as I said, each channel symbol conveys 1 sync bit and 1 data bit, so 2 bits per frame essentially. So every shift in the frequency is giving you or transition is giving you 2 bits. The transmissions normally start 1 second into an even UTC minute. So this is really key. To operate effectively in Wspr, you need good frequency stability so that you're not moving around. Since you only have 6 hertz to give, you can't move around much. But you also have to have a very good source of time. As it turns out, GPS receiver modules for time synchronization, not time measurement or frequency sync, but as location standards, give you 1 pulse per second anyway. Just about all of them do. And they've gotten to be dirt cheap nowadays. So adding a GPS receiver into the mix for a Wspr transmitter is a pretty inexpensive proposition. The minimum signal to noise for reception, I have violated this a number of times, or I will say I've been spotted a number of times deeper into the noise than 28 dB, but that's sort of the thumb standard to try to say here's what a good minimal discernible signal level should be, is 28 dB into the noise. Typically in practice you run anywhere from a few dB above to about 30 dB in the noise. Okay, and of course the noise is on the spotter's end, the reporter's end, based on local conditions and whatnot. Not like that's going to be standard, and of course varies with the atmospheric conditions and such, so mileage varies. To put a real number around that, Wspr signals are typically running at about S1 to S2, sometimes S3 if we're talking Wisconsin to Minnesota or Iowa to Minnesota. But you're down there near the post on the meter. All right, so forward error correction, this big blurb of words. Well, it's essentially about taking a block of data. And why 32 bits? Well, processors are going to be 16-bit, 32-bit, 64-bit, or 8. They're going to have registers, and 32 actually turns out for integers to be a convenient number. When you're trying to split up, jumping ahead a little bit, when you're trying to split up a 50-bit piece of information, you're going to extend it, as I said earlier, because of parity, but also you're trying to fit it into 32 bits. Well, 50 doesn't fit into 32. 50 can fit into 64, right? But that doesn't allow for much in the way of redundant error correction or error detection bits, parity bits. So you end up with a bit length of 81, and the redundant bits for an 81-bit message end up being 81 more, so you end up with a complete message length of 162 bits. Those are broken up into 162 frames, and every transmission frame then goes for, which I get into in the modulation section here, so maybe I won't jump ahead on that. But the bits have to be put into a 32-bit register. You may have a couple of them. You certainly should have a couple of them available to you in a microcontroller or microprocessor. Shifted 1 bit position and XORed with 2 constant values, which are on here. Hex E4 613 Charlie 47 and hex Fox 2 Dog 05351. Why those numbers? There's some history, but they're kind of random. Okay. The point was is they had to have a convention. If everybody's implementing the same algorithm everywhere, then everybody can expect the messages to be decoded the same way. Okay? So you could think of it as almost the same as having a public key, where to have the message be decrypted, you have to have a public key, so on and so forth. So it's not for cryptography reasons, but it's convenient to be able to encode or scrunch up the bits to put the messages together. The R value in that for the rate of 1/2 simply ends up being 81 over 162 as a ratio, right? So there's twice as many bits that are transmitted than had to be transmitted, if you will. All right, so there's double the number of redundant bits. Okay, so we have a keying rate that has to do with the offset and how quickly we can turn things around realistically and then shift a minimal amount. And then we have to think about, okay, where do I get how do I shift each frame, the frequency? And that gets into the modulation. And those 4 tones are spaced, as I said earlier, 1.4648 hertz apart from each other. So you can actually have a sequence, for example, of 1497.803 hertz, 1499, 1500, 1502, so on and so forth. The sequence, the way they run, is predefined. So the way you run through the tone shifts is predefined as well. The sequence starts off as frame 3, which would be the 1502.197 hertz frame in this example. Frame 3 again, frame 2, frame 0, frame 2, frame 0, frame 2, frame 1, and so forth, okay? That framing or that shifting is also well known. It's part of the spec. So when those bits are being shifted around, the transitions are being made, there's an algorithm to be able to rotate through the shifts. Even though you have to represent different data different ways to get the ones and zeros essentially out that represent the message, the shifting sequence has to be somewhat predictable as well. The occupied bandwidth, as I said, is 4 shifts at 1.4648 hertz, so about 5.8592 hertz, or about 6 hertz. So it's very efficient, very tight. The big thing about Wspr is what you can do with it in terms of miles per watt. Now, as you'll see, my record one so far was over to by Australia in New Zealand. That was 9,053 miles on 0.2 of a watt. And in miles per watt, that's 9,000 miles times 5, or 45,000 miles per watt. So, yeah, you can go around the world a couple times.
And you learn Australia's open way more often than we think it is.
Yeah, yeah. Well, especially in the morning. The gray line propagation effect, where you're at dawn or at dusk, is very easy to see with Wspr. Because what ends up happening is you might get anywhere from 500 to 1,000 miles during the day, and then all of a sudden your distance creeps up at dusk. And then it subsides again because those F layers are coming down at night, cooling off. Yeah, but then in the morning, as the sun comes up, things are heating back up, and you're getting the spreading of the ionosphere again, and then all of a sudden the mileage goes up again before it falls back down. So one of the things that Joe Taylor was trying to get a handle on was being able to gauge very accurately what the ionosphere was looking like from an RF propagation perspective. As this has taken off, there are 1 million reports per day now on Wspr. So with all the beacons and people just doing this ad hoc in the evening, there's 1 million plus of these being processed every day and put into the log, which is amazing. So it has taken off worldwide. You have reporters all over the place, transmitter beacons all over the place. I go back and forth between my SDR as a reporter and a transmitter in other cases. Whereas before I used to play both roles on my transceiver. Now I have 2 dedicated instruments to do each role. Not simultaneously, obviously, but I can't even go back and forth at this point yet automatically. But you don't want to retransmit on Wspr more than about 10-second intervals. There are some, again, that's convention. There are some people that do it every 5 minutes, every 2 minutes, kind of extreme. But the guideline is to go about 10 minutes between transmissions. That allows the 2 minutes for the transmission and about 8 minutes kind of a rest time before that fires up again. The speed at which the reporter can get your spot in the log is going to happen very quickly. It's going to happen in milliseconds. It's going to come over the internet. It's going to go into the Wspr database very quickly. So when you're done with your transmission, for example, if you click refresh on the browser, on the page that we're looking at here, it's there. So it's a nice system, very nice system. Yes, Chuck?
I noticed the frequency is 7.040.
Yep.
Didn't that used to be the QRP calling frequency?
Yeah, that's right.
And now it's shifted more to the Wspr?
It's shifted up a little bit, so the center is, that's a great question, the 7040-100 is the center of the Wspr band. So bear in mind that that's not the dial frequency, okay? It's offset up from the dial frequency of 138.50. So there are PSK 31 and CW ops on either side of where Wspr sits. Again, at only 200 hertz of bandwidth, all right? But again, as usual, by convention, people have kind of stayed away from these areas for the most part, yeah. Yeah, but good point. The other thing that you can see on this is that even though I run at 7040-070, actually, most of the time, I'm being spotted all over the place. Why is that? Well, every reporter's frequency on the receiver is going to be just a little different than mine. Okay, now mine's GPS locked. Not to say that mine's exactly right, everybody else is wrong, right? But it's stable, right? That's the big thing, is that it's stable. As that varies over the day, I'll have people spot me exactly on 70, and it's always the same people. And I'll see people spot me at 71, for example, or 69, and it's always those same people, right? So you can tell that it's just like when the ARRL has the frequency spot contest. You're going to get a few dozen hertz of variation across all the ham receivers out there. Different kind of equipment, different ages, different everything. So that's really why you can get into that. The other reason is if you have a very bad transmitter, it's harmonics. So if you get into a situation where you're transmitting, and this is usually higher power, with essentially a square wave coming off of a Raspberry Pi, you can get spotted on multiple bands because, as we all know, 40 goes to 20 and then to 10. Now 10 you don't have to worry about so much, but if you're at 40, you're going to get spotted on that kind of transmitter on 20 as well. So you get 2 for 1, essentially.
So that's the spotting frequency.
Right, that's the spotting frequency, and that's the wrong kind of 2 for 1. The FCC has commented on Wspr before because of its homebrew sort of nature, and unlike sinusoidal CW transmitters that are usually pretty clean or relatively clean, the thing that saves Wspr, I think, is its relative power levels. As I said earlier, I've seen people on at plus 47 dBm, as I recall, it's 100 watts. That's a mistake. That's just somebody just forgetting to turn their power down, because generally people run at about 5 watts. Okay? On average, they're running at 5 watts or a little lower. I've seen as low as 0.02 watts. Okay, so about 3 to 6 dBm, somewhere in there. So you can get spotted on incredibly low power. That's where I'm taking this next, is to dial it down from 23 dBm down to see how far I can get on lower power. But it was an eye-opener for me because while I knew CW could give you a lot of miles per watt, I didn't really appreciate that 0.2 watt could get you around the world.
30 meters in Wspr, you can work halfway around the world every day.
Yeah. Yeah, that's
reliably.
That's the
day.
difference between 30 meters on Wspr and 40 meters. 40 meters will get you more distance, but 30's open 24/7. It's kind of like the difference between 20 and 40. You go up a little bit towards 20, you start to get into some pretty favorable conditions around the clock. But ironically, 20 on Wspr suffers from some other problems, mainly signal to noise ratio, because 20 tends to be noisier than 30 or 40.
So if you get in the middle of a CW contest, does this just all get wiped out?
It can, yeah, it can, yeah. I've definitely seen it, and I picked this slide for that kind of reason. Here we have JT65 on the left of the text here. And then we've got PSK31 where it isn't supposed to be. But the center is sitting right in here, I believe right there. And you only should be about 200 hertz either way. You know, there are people that run Wspr outside of the standard 200 hertz and never get spotted. So it's a mistake. If you run outside of the spot range, it's not like somebody's going to slap your hands, but you'll never be spotted either. It's just, that's the way it works. The other thing that you'll see is something like this. When you see a snake, that's drift. So during their message transmitter, on transmit, they were drifting. And more often than not, it's because of heat. Right? So their oscillator isn't isolated from their finals or something in the power supply or something. It's causing some heat and causing the frequency shift. It can be a fan turning on. It can be some very subtle things. One of the things I'm learning in this realm is stuff that I've only read about in a hands-on way. Literally a breath across a crystal will shift it enough to matter in Wspr.
Window open in your office?
Yep. Yeah, my door. When my door opens, I can see it in my drift. When I'm at work, I know someone's opened the door to my office because it'll drift to minus and then go right back to zero.
Burglar alarm.
What's that?
Burglar alarm.
It's a burglar. Well, yeah, not a very good one, but so what you're really after are these kind of trails where they're pretty much straight down. You'll see some that start off and drift and correct, but generally speaking, most of them are very close to zero drift. Again, with the GPS modules, helping the oscillators discipline, okay, which is its own topic, but essentially what they're doing is taking an accurate pulse per second spacing to within nanoseconds from the GPS modules, and they're taking the frequency that they're disciplining, dividing it out so they get down to 1 pulse per second, and then they're comparing those and then shifting a voltage for a VCO, either through a digital analog converter or by some ways to get that voltage to drift. The other thing is the huff and puff method that's used as well. So there's a couple of ways that they try to get the stability. And as I mentioned earlier, the housing a temperature compensated crystal oscillator is really important for stability. You see it in GPS disciplined oscillators for a 10 megahertz reference frequency that's good to 9 places past the decimal point. You see it in some rigs, you're starting to see it more for the software-defined rigs, where you've got essentially a very tightly controlled oscillator frequency somewhere in your PLL, right, circuitry that's going to hold that stability. Because really all the digital modes need that, but Wspr is probably the most sensitive to it right now. So what does it require, just to sum up here? It requires time accuracy so that the starter frame happens when the reporters are expecting it. The end is not so much an important thing because it ends before the 2-minute window shuts. And frequency accuracy and stability. Those are the two things really that you need. You don't need a lot of power. So since this club has roots in QRP, you know, it's the kind of thing that fits right into to what we've done in the past. The cost of the kits to do this or to roll your own and build it yourself, there's plenty of circuits out there. There's plenty of examples. And this kit, I think we spent, I want to say, what, $50 to get started with
Which
it.
one were you using?
The QRP Labs Wspr version 3S, I think it was. So it's the latest rev.
The 5351 version?
Yeah, it's Hans Sommer's 5351 is the synthesizer, right? Exactly.
This
Yeah,
sounds very nice, except I don't own the place where I live, so putting up a good antenna is difficult. What kind of antennas are you using, and et cetera, et cetera?
I won't kid you. I've got an antenna that's 22 feet off the ground from its lowest dip point. It's a horizontal wire that's an off-center fed. It's a really good antenna. I mean, I paid I think $100 for it, so it was not an inexpensive antenna. But it performs like none other that I had. I used OCFs and NFEDs before in straight dipoles. And that's a 40-meter half wave, so you basically have 20 meters of run that you have to have, you know, which is diagonal across my urban neighborhood backyard, right? So that's as big as an antenna as I could fit in. But NFED ZEPs, for example, work very well with this. A lot of people that run them. And in that case, you can run as a sloper, and then you just need to be up high enough to run up. At 30 meters, you need 15 for a half wave. At 20 meters, you know, you need 10. So if you go up in frequency, you won't get the distance, but you certainly could get a wire. You know, it starts to become more realistic.